All right. Welcome to chapter 7, what are we on? Like 6 now? Holy smokes. So now that we have talked through kind of the quantum numbers, the N, L, M sub L, those main 3 quantum numbers that will bring us to describing one specific orbital. There's a couple different ways that those orbitals can be shown and drawn and used. So what you see in what we talked about in chemistry is like for something in the 3rd energy level, we would draw something called an orbital diagram. And in an orbital diagram, what you're going to see are boxes. So you'll see the 1s orbital, and then you'll see the 2s orbital, and then you'll see 3 boxes labeled 2p, and those represent, each one of those boxes represents the 3 2p orbitals. So 2px, 2py, 2pz, each one of those is an orbital. And then you'll see the 3s orbital, and then again, you'll see 3 of the 3p orbitals, all 3 of the orbitals. And then it keeps going on and on like that. So that's called an orbital diagram. And when we fill in the orbital diagram for a specific element, you're going to see, like, let's say we do this for sulfur, for example, you're going to see a couple rules that are followed. And one of the rules is that each of the orbitals can contain up to 2 electrons. So if we were talking about hydrogen, for example, in the hydrogen orbital, hydrogen only has 1 electron. So it is okay to put just 1 electron in the box. We only have 1 electron. We don't want to put more than 1 electron in the box. But for sulfur has 16 electrons. And so you can put up to 2 electrons per box. Another thing that you'll notice is at the lower level energy orbitals need to be completely filled before you move up in energy levels. So like I need to completely fill the 1s orbital before I can put an electron into the 2s orbital. Now, before we kind of fill this up for all 16 of sulfur's electrons, there's a couple other things that we need to talk about, a couple other rules. And one of them is more easily shown if you look at the orbital diagram in terms of energy. So that's what you're going to see down here at the bottom of the page. This is more of an energy diagram view. You'll see the arrow on the side over here that has the E. And so at the bottom would be low energy orbitals, and the top would be more like high energy orbitals. And so you can see the exact same pattern, only they are ranked in terms of energy. So down here we have a 1s orbital, and then we have a 2s orbital. And then notice here we have so this represents it with 3 dots. You can also do 3 lines, and that would be your 2p orbitals. And when you're filling them, you're going to fill them the same way. If I have hydrogen, and hydrogen only has 1 electron, I'm just going to put 1 electron in there, and that's okay. But each one of those lines, just like each one of the boxes, represents 1 orbital, and so they can fill up to 2 electrons. So if I'm dealing with like lithium, which has 3 electrons, I would put 2 electrons in that 1s orbital and then 1 electron in the 2s orbital to give me 3 full electrons. Okay, now, so notice again, we're filling each orbital with 2 electrons before we go to the next higher energy electron. Now notice the 2p orbitals here, all 3 of them are at the same energy level. So we have a term for that. That is called degenerate. They are degenerate orbitals. So I know in society, degenerate has a really negative connotation that has nothing to do with energy. But in science, degenerate is merely a descriptive term that means they all have the same energy. So if you have 3 little toddlers and they all have the same energy level, you can call them all degenerates. Just maybe explain to the parents what you're talking about so they don't get all offended. So all 3p orbitals have the same energy. And so it doesn't matter which one the electron goes into. And actually, since they have the 3 different orbitals and electrons do not like to be near each other, the electrons are actually going to spread out. So if we're talking about, let's see, carbon, for example, carbon has 6 electrons. We would put 1, 2 in the 1s. We'd put 1, 2 in the 2s orbital. And then we'd put 4 and 5 in 2 different 2p orbitals. I love Miss Searing's term for this. She calls this the smelly bus rule. You know, if all seats on the bus are equal and everybody's smelly, you're not going to sit next to each other. You're all going to spread out and sit in your own seats, right? That's exactly what the electrons are doing. They don't like to be by each other. They're all negatively charged. They're going to repel each other. So they're going to spread out as far as they possibly can without moving up in energy levels. And so if you just have those 6 electrons for carbon, then the 2 electrons that are going to go into the 2p orbital are going to go into different orbitals, not the same orbital. So let's keep going. Let's say we have oxygen. Oxygen has 8 electrons. So we go 1, 2, 3, 4, 5, 6, 7. Now we have one more electron, and its option is to pair in the 2p orbital or to move up into the 3s orbital. So electrons would rather pair than move up. So the 8th electron is going to go pair up in the 2p orbital. So that would be electron 8. And you won't actually have an electron in the 3s orbital until you get to sodium. So it would take 9, 10, 11 electrons until you actually get one to move up into that 3s orbital. So 2 electrons per box. Electrons are going to fill the lowest boxes, the lowest orbitals, before they move up in energy. And electrons will spread out as long as they can do so without moving up in the energy levels. So when we're talking about high energy versus low energy orbitals, what we're really talking about is a distance thing to the nucleus. So let's just take a minute there, and before we talk about other things, let's talk about this distance idea. So if you have a nucleus here and you have a whole bunch of energy levels that are going out from that nucleus, you need to think about this in terms of potential energy. So if we think about this as if it's like books being stacked up, right? What is more stable? One book sitting on the floor or a whole stack of books? Well, let's make this a little more dangerous than sitting on the floor. One book being held by me or a whole stack of books being held by me. Which one of those is a lower energy system? Which one of those is a more stable system? And obviously, one book being held by me is a more stable system. It's a lower energy system. The higher up you stack things, the higher the potential energy is, right? So closer to the nucleus, lower energy, more stable. That's kind of the connection you should go. So closer to the nucleus, lower energy, more stable. If you promote your electron to get an electron to go all the way out there, you actually remember that electron has to absorb energy. So it takes on energy farther from the nucleus, high energy, less stable. This is kind of a theme that you'll see in chemistry. So it's the same thing with the energy diagram. The energy orbitals, the orbitals that are closer to the nucleus are considered low energy orbitals. If you get the higher and higher and higher you go in energy, the farther away you get from the nucleus. So in addition to this arrow being energy from low to high, you can also think about it in terms of distance. Close to the nucleus, far from the nucleus. Okay, so the low energy, if you have all the electrons in the lowest possible arrangement, like here, what we currently have drawn here is the lowest possible energy diagram for sodium. We would call this the ground state. The ground state is when all the electrons are as close as they possibly can be, or as low energy as they possibly can be. If you have an excited state, then one of these electrons has been taken out of its lowest possible scenario, and it's been promoted to a higher energy orbital where it shouldn't be existing, right? And that is not a stable arrangement. That is a reactive arrangement. Something is going to happen there. The electron's going to fall down and give off energy. Or maybe this atom is going to react with something else. So lower energy, more stable. Higher energy, less stable. Those higher energy orbitals we would call excited states. If you have what we have right now, where sodium has an electron in a higher energy orbital, that would be considered an excited state. Okay, something else that I've kind of been doing, but I haven't actually been explaining, is kind of the fourth rule for filling electrons into orbitals. And that rule has to do with the magnetic spin quantum number, our very last quantum number. So in our magnetic spin quantum number, this quantum number is kind of unusual. It's not like the other three quantum numbers that are all dependent on each other. The magnetic spin quantum number really has two options. So m sub s, it can be either plus a half or it can be minus a half. So what this is referring to is it's referring to the direction in which the electron is spinning. So the electron can be spinning up, and we would draw that as an up arrow. Or since we're drawing so many arrows, we draw them as half arrows. Or the electron can be spinning down. And again, we would draw that as a down arrow, or because we draw so many arrows, you can draw it as like a half arrow spinning down. So that's why I drew, you can see up here with like sulfur, I drew these two electrons up here as like with pointed ends, because when electrons fill into the same orbital, they're either spinning up or down. If one's spinning up, the next one has to spin down. You cannot fit two electrons into the same orbital that are both spinning up. And electron spin is fascinating. And actually, there's a whole host of technologies that are based off electron spin. And MRI is one of them. If you've ever gone to the hospital and had an MRI, you go into this long tube and you sit there and there's all these like clicking noises. And what they're doing is they're spinning magnets around your body. And the like computer that's in there is actually detecting magnetic spin. It's like manipulating the magnetic spin that's in your body. And as a result of the magnetic spins and what it's like manipulating and what it's detecting, it actually can build a picture of your internal self from electron spin. Super cool. I actually don't understand the technology very well at all, but I think it's fascinating that the whole technology is based off of this kind of idea. I'd love to learn more about it in the future. So electron spin, it affects other things too, We'll talk about later on, once we go through the bonding, we'll talk about how electron spin affects magnetism, and we'll look at some examples of those as well. Okay, so at this point in time, you should have all the rules for filling electrons into orbitals. The one more thing you need is the order of the orbitals. So we talked about how electrons fill from low energy to high energy orbitals. Well, here's the catch. You got to know that order, right? If you're going to fill in electrons and predict how electrons are going to fill from low energy to high energy, you need to know that order. And so there's a couple tricks for figuring out that order. And we actually talked about these in chemistry a while ago. So let's kind of review some of these tricks for talking about what order the orbitals go in. What is that low energy to high energy orbital order? Okay, so one of the ways that you can know the order of orbitals from low to high is there's a little chart that you can make. If you list off all the suborbitals in the order of their energy levels and put diagonal lines through them, this will give you the order of low energy to high energy. So we're going to list off the suborbitals in the lines of their energy levels. Oops, not a P. Apparently, I can't do this and talk at the same time, so give me a second. 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 6s, 6p, 6d, 7s, 7p. I think that should get us there. Let's just add a 7d in just for fun. Maybe a 6f too. Okay, so anyway, here's energy level 1, energy level 2, energy level 3, energy level 4. Also, one thing you may note is I only listed the allowable energies. So remember how we talked about how if n is equal to 1, that would be the first energy level. That means L can be anything from 0 to n minus 1. And the only option for L in the first energy level is L equals 0, which is S, right? So in the first energy level, only one shape exists, and it is the S shape. And the S shape is a sphere. So notice over here in the first energy level, I only have one shape or one subshell listed. Whereas in the second energy level, I have both allowable shapes listed. The other thing you can do is if you just make it a triangle, then you've covered your bases and you don't even have to think about all of these little equations. Okay, so now what we're going to do is draw slashy lines through all of these. And that will give us our order of filling. So 1s fills first, then 2s, then 2p, then 3s, then 3p. And all of this we have predicted so far, right? Of course, 1s, 2s, 2p, 3s, 3p. But what people want to do next is say 3d will fill next. And that's not actually what happens. 4s is the next thing that fills. 4s actually fills before 3d. And this is because, remember, as we're getting into higher and higher energy levels, we are getting more and more and more electrons, which means you're getting more electron interference. So draw back from that like salt on a speaker experiment as we're watching the salt on the speaker. As our pitch goes higher, we get smaller waves, and so we get more waves interacting, and these patterns become more and more and more complicated, right? Well, the exact same thing is happening with our our like solutions to the Schrodinger equation, those probability map pictures. As you get more electrons, those electrons have more and more and more and more possible interferences. And therefore, you're going to get a more and more and more complicated picture. And it does some things that we wouldn't necessarily, think that it would do, like it's going to push the 4s to a lower energy level, and the 3d orbital is going to be pushed into a higher energy level. So that's why you need some trick to memorize or figure out the order that these orbitals fill in, because it's not as straightforward as you might think because of the interference patterns with all of these electrons being forced into the same little area. So 4s will fill, then 3d, then 4p, 5s, 4d, and it just kind of goes on and on and on. But as long as you follow that diagonal line, you're going to be able to predict the order of filling. Now, here's the catch. I don't love this because in the middle of a test, I don't want to sit down and draw this whole thing out and make sure my rows line up and make sure my slashy lines line up. That's definitely not ideal. And so I like to use the periodic table. The periodic table is going to give you the exact same pattern as long as you know how to use it. So let me quickly show you how to kind of get the same exact information off the periodic table. Again, this should be a review from chemistry, and then we can kind of use that tool going forward, and you'll have a couple different options as to how you want to remember this. All right, so here's our beloved periodic table. Now, there's a couple things you have to know in order to use this. So the first thing you have to know is that each row corresponds to an energy level. So this first row corresponds to the first energy level. The second row corresponds to the second energy level. And if we think about that energy level diagram, 1s, 2s, 2p, notice that the 1s orbital can hold 2 electrons. So here's electron 1 and here's electron 2. And the 2s can hold 2 electrons. So here's electron 3 and electron 4. Right? Okay, so all of those electrons are going into the S block. Now, if we keep going across the periodic table, filling in our ground state orbital diagrams, you're going to start to see some patterns. So 2p would be able to hold electron 5, 6, 7, 8, 9, 10. 5, 6, 7, 8, 9, 10. And then electron 11 is going to come back to the S orbital. And electrons, oh, I forgot to put them in my orbital diagram. There we go. Okay, electrons 13, 14, 15, 16, 17, 18 are going to be in my p orbital. Okay, so hopefully you start to see a pattern. Everything in the s orbital, you'll notice, is collected into one area. So this, remember from chemistry, is called what again? It's your S block, right? And notice that S orbitals can hold 2 electrons. The S block is two elements side to side. The P orbital can hold 6 electrons, and the P block, 1, 2, 3, 4, 5, 6, is 6 elements over. Okay, so if we go to the Ds, remember Ds have 5 orientations, can hold 10 electrons total. And check this out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this over here is our D block. Can hold 10 electrons and is 10 elements across. And then down here, this is our F block. Now, it can hold 14 electrons. It should be 14 elements over, but depending how the periodic table is set up, sometimes it is and sometimes it's not. Like notice this periodic table pulls out an electron or an element here. So instead of this Lu being in the D block like it's supposed to, this periodic table has decided to pull it out and put it in the F block. So not everybody sets up their periodic table with the SPDF blocks in mind. So if they do, then you'll get 14 down here in the D block. If they do not, then you might get 13 or 15 down here in the D block. Everyone kind of has their own industry and their own purpose for the periodic table and why it's useful to them. So everybody might set it up a little bit differently anyway. And the F block tends to be, there are crazy shapes, right? So the F block tends to be a little bit crazy anyway and doesn't necessarily line up with everything we want it to line up with. Anyway, if you can label the rows as energy levels and you can label these 4 blocks, then this periodic table becomes your order of orbital filling. Let me just circle that one more time. So here's S, P, I forget what color D was, maybe purple, D, F. Okay, so if I want to know, let's go back to, let's do, I don't know, sulfur. Let's go back to sulfur over here. If I want to know what that orbital diagram for sulfur looks like, all I have to do is count over. So I go, here's 1, 2 electrons. They're in the first row. So they're in the 1 first energy level, shape is S, and there's 2 of them. Okay, now 3 and 4 are going to be in the second energy level, shape is S, and there's 2 of them. Now 5, 6, 7, 8, 9, 10 are going to be in the second row, the P shape, and there's 6 of them. And 11, 12 back in the third energy level, S shape, there's 2 of them. And then we have 1, 2, 3, 4 in this third energy level, P block, and there's 4 of them. So 1, 2, 3, 4. So there's our orbital diagram for sulfur. And I remembered the order that the orbitals fill in just by following along the rows and the blocks on the periodic table. Now, you may pick up and be like, Martins, why are we drawing boxes? There's an easier way to do this. And you are right. It's called an electron configuration. And guess what? All of this has set us up for electron configurations. So that's where we're going to go next. But you'll have to hold all that excitement inside your heart because we are going to do that next class. Okay. Have a good night.